Hi. So in this video, we're going to prove that the analytic rank is subadditive. So this is a continuation of the previous video. So you should watch that one if you don't know all the definitions. I can recall some of them just for the analytic rank. And I'll also recall, yeah, and the bias. So let's just get started. So, well, and I'll even say what subadditivity is, which is what we're trying to show. So recall, so if T is an order D tensor, okay, then we define the bias of T to be the expected value over all x1 up to xd in V of chi of T x1 up to xd. Okay, where chi here is a non-trivial additive character, it doesn't matter which. And we also showed in the previous video that this is the same as it's the probability over all x2 up to xd in V, the probability that this linear form, x1, well, x2, I guess, up to xd is identically 0. All right, so there's a linear form in x1 because we've already fixed x2 up through xd, and the probability that this linear form is 0, that's the same as the bias. Okay, so then the analytic rank, ARKT, is defined to be minus log f of the bias. And we showed that the analytic rank is non-negative in the previous video. Okay, and we also showed that it's equivalent to ordinary rank for a 2 tensor, which is a matrix. Okay, so in this video we're going to prove something called subadditivity. So subadditivity. Okay, and this is what we kind of want to show. The analytic rank of T plus S is less than or equal to the analytic rank of T plus the analytic rank of S. Okay, so to do that, we're going to first need 2 lemmas, and let's just get started. So this is the first lemma, called lemma 1. Okay, let W1 through Wn, or I guess here, let's put a W0. It's also W0. Be functions from f to the m to f. All right, so there's n of them, well, n plus 1 of them, and they're from f to the m to f. Be functions, yeah, be any functions. Okay, so let functions a and b be defined, and they're going to be from f to the n cross f to the m to f, given by, so a of x, y is going to be the sum of I equals 1 to n of x, I, w, I, y. Okay, so xi is the ith coordinate of x. So x is going to be a vector in f to the n. And b xy is axy plus this w naught of y. All right, so you have kind of a sum here that depends on both the inputs. It depends on both the inputs x and y, but b has this term that doesn't depend on x at all. Okay. Then the bias of b is less than or equal to, the norm of the bias is less than or equal to the bias. Okay. So this it's not a difficult proof. So the proof is we just expand. Okay, so we expand the bias of b. Well, what is that? That's, you take this average, and we're going to write it in this way. So we're going to, yeah, so x to and f to the m, n, plus the value of y and f to the m of chi of b of y. Okay, so nothing special yet, that's just the definition. Then, so now here we pull the x inside and we take expectation of y in f to the m of the indicator that wiy is equal to, or w1, sorry, w1y is equal to all the way up to w, how many? There are n of them, right? N y is equal to 0. Okay, and you times that by chi of w naught y. And why is that? Well, it's because this b here is a sum, right? And because it's an additive character, the chi of a sum is the product of the chi's. So now you have a product of axy being 0, right? So I mean that's a sum, sorry, of n terms, and so each of these is we need each of these to be 0, and that's 0 if wiy is 0. Okay, does that make sense? I mean, if the expectation of x to the FCM is of this thing is 0 when wiy is 0. Okay, so that's where that comes from. And then we just, well, I mean, by the triangle inequality, the bias of b is less than or equal to expected value of y in f to the m. Okay, we pull it inside. I mean, pull the absolute values inside, and it's just 1 of wiy wny is equal to 0, and this is the norm of this chi is just 1, right? So, and that is, I mean, this is equal to the bias of a, and that's just because this is a linear. So this is the same as saying that this is a probability that a linear form is identically 0, like we set up here, right? So the bias, there's two variables, x and y, and it's a linear form. This is 0. All of these are 0 if and only if the linear form on x is 0. Okay, so that's the bias of a, and that's so we're done. Okay, so then this lemma is going to be used to prove another bound, and this bound's a little bit more complicated, and we're going to need some notation. Okay, so notation. Okay, so fix some d. Okay, and we have x with this little vector thing is x1 up to xd, and same for y. y1 to yd. Okay. And then for I subset of d of 1 through d, okay, we let this is I complement be with respect to the ground set d. Okay, and xi is the set of all xi's for I in I. Okay, so we kind of saw that with the partition rank above, right? So like this is going to be a vector with the size of I elements, and we can index them by the elements of I. Okay, so lemma 2. This is a pretty important lemma, actually. This lemma will be used in the next video too. So so kind of like a lot of the like sort of the legwork is done by this lemma. So let d greater than 1 be given, and for each I subset of d, okay, let Ri be any order I tensor, order size of I, so be an order size of I tensor. Okay, now consider the function r, okay, and it's going to be on a vector x, it's defined in terms of these ri's. So it's all I subset of d, ri, so that's the functions that were given, and xi, which is up here, this thing up here, because ri needs a vector, like it'll take in a vector with size of I elements, indexed by I, sorry, and then so that's what we need. Okay. So what are we trying to say? Then the bias of R is less than or equal to the bias of R D. Okay, and this is not a sum. This is a single function. This is one of the this is one of these functions that we have. Okay, for each I. So we have 2 to the D functions Ri. Okay, and we're just saying that like the biggest one, the only one that is a D tensor, the bias of this big sum is less than the bias of just that one order D tensor. Okay. Okay, so how do we prove this? Oops. So proof. Okay, so we fix some I in D. Okay, and now we can write big sum Rx as sorry, let's keep that. The sum of all I that contain, that contain I, let's write this way, Ri x I, plus the sum of I that don't contain I, Ri x sub I. Okay? Now, if we setting x to be xi, so just a single, this is just a single number, or it's in, sorry, because xi, yeah, it's an element of, what did I write? I wrote v here, but I think what I meant was, yeah, no, that's fine. So it's a single element of one of the v's, which is f to the n. Okay, so setting x equals xi, and where am I? Y equals x d minus I, so it's d minus 1 vector. The first sum has the form sum of I equals 1 to n xi wi y, right? And the second does not depend on x at all. So we can let it be w0 of y. Okay, so wait, sorry, I mean that's a lot maybe. Let's unpack this. So this sum up here is an order 1 tensor of and we know that xi is in there. Sorry, it's not an order 1 tensor. It's an order size of I tensor, like each of these terms. But xi is we have xi times some function of y in there. Right? Okay, and so now by and then on the right hand side, it's very easy to see that it doesn't depend on x at all because xi never shows up in this sum. Okay, so that's going to be w0. Okay, and so now by the previous lemma, Okay, the bias, the bias of R is less than or equal to the bias of this sum, so I in I of R I X X I. Okay, so this is this is A X Y, right? In the previous lemma. Okay, and then now all we need to do is we need to whittle this down, kind of, right? And so we just so we iterate with I equals D all the way down to I equals 1. To I equals 1. Okay. To get, then this thing can be bounded above again. So, I mean, this is D and I, right? And then now you do it again with, because this thing now, for everything, all the i's that contain D, that's like all the subsets of 1 through D minus 1. So we just repeat and we put D minus 1 there and D becomes D minus 1. And then you just keep going until you just have one set on the right hand side. Okay, the R sub D, R sub square bracket D on the right hand side. Okay, and so that proves this lemma. Okay. Now, one more thing before proving subadditivity, we need one more bit of notation. So notation again. For I, subset of D, let T I X Y. I mean, this is with respect to some tensor T, be T of X sub I, Y sub I complement. And that's the same as saying T of Z1 up to ZD, where Zi is equal to Xi if I is in I, and Zi is equal to Yi if I is not in I. Okay, and so page. So expanding out the definition of multilinearity, we see that T, I keep writing on instead of T of X plus Y, okay, because this is in every variable, so it's linear in every variable, and we need to, like, it's going to be a bigger sum than just T of X plus T of Y, right? So it's actually this sum, I subset of D, okay, T I X Y, okay, because we need every single possibility of whether you pick X or you pick Y in a certain variable. Okay, so it's going to come in handy later. All right, so now we're going to prove subadditivity. So theorem 3, subadditivity. Okay, so what's the precise statement? Let T and S from V to the D to F be order D tensors. Then the analytic rank of T plus S is less than or equal to the analytic rank of T plus the analytic rank of S. Okay, so proof. Well, it's enough to show that the bias of T plus S is greater than the bias of T times the bias of S, because the analytic rank is the negative log of the bias. Okay, so let's expand this out. So we express, we'll expand out the right hand side. Bias T bias S. So what is that? That's just the expected value of all x in VD of chi of t of x. And I'll use a different variable for the s part. So we use y in VD chi of s of y. Let's see, we have space. There's another bracket here. Okay. Now, now we pull everything together. We see that this is expected value of x in VD, expected value of y in VD, and then you the product of two of chi times something times chi times something else, because it's an additive character, is chi of t of x plus s of y. And this is the same as here, the same distribution as x. It's not tilde, that's in VD. Y in VD, chi of t of x plus s of x plus y, right? Because x plus something, that's a bijection. Okay, and then this is, by definition of bias, is the bias of t of x plus s of x plus y. Okay. So now, by the earlier decomposition up here, this thing up here, right? So s of a sum, okay, splits up into this sum overall subsets I of d. This I of square bracket d. Okay, so we can do that. So by the earlier decomposition, okay, we have bias t, bias s is equal to the bias of t of x plus this sum I subset of d si of x plus not x plus y, right? This is now the notation we established earlier of that. Okay, and now let's pull this out. So we have one term in here. There's one term in here that's just t of y, if I'm not wrong, right? Or sorry, just s. There's one term in here that's just s of x. So here, let me just write it. T of x, sorry, not t. We want to prove a bound on t plus s, right? So it would be really nice if we can get a t plus s somewhere in here, and we can by doing this. So t plus s, and then on this side, it's all I that are not equal to d, because we took out the d of s, I, x, y. Okay. So now let's get rid of y here, right? By just making this as big as possible. So setting y to be equal to some b in VD that maximizes the norm of this. By this I mean this whole thing here. We have so let's see. So it's bias of t bias of s for this b is less than the norm of bias t plus s. What have I done? I messed up some brackets, so I'm pretty sure this has got to be big. Bias of t plus s x plus sum. So I'm still getting used to this tablet thing. Sum of I not equal to d s I x b. That's all that changed here. Have I put enough brackets? Okay. So here, now the reason this b is useful is because now si x b is an order size of I tensor. Okay, in the variables xi, right? Remember that for all variables indexed by I, it's x, and then for all the other ones it's b. So there's size of I many variables. So it's a page. Okay, and so now we can apply the previous lemma. So we apply previous lemma because this is a sum, right? This is kind of like R of x in the previous lemma. So we apply the previous lemma with RD is the one that uses up all the variables. So that's x. And for all I, Ri x sub I is equal to Si xb for I not equal to D. Okay, and that tells us that, well, do I need to write it out? So I mean bias T, bias S is less than equal to like this thing, which is less than equal to, I'm not gonna write it, which is less than equal to bias T plus S. Yeah, bias R sub D, okay? And that's all we needed to show. So we proved that the analytic rank is subadditive. Okay, and I'll just finish with like a little corollary, which is it proves a correlation inequality on common roots of tensors. So I mean, it has nothing to do with anything else, but just shows that this is actually useful, not just as a lemma for the next result, but just in and of itself. So corollary, that T1 up to Tm, S1 up to Sn, from V to the D to F, be order D tensors. Okay, then, okay, so they're going to be correlated. That means that, positively correlated, that means that if T1 of x, or the probability that T1 of x, basically that everything is 0 equals S1 of x equals Sn of x equals 0, okay, is greater than equal to the probability that you take some subset, so that's where T and S, T1 of x equals Tm of x equals 0, and times the probability that S1 of x, Sn of x equals 0. Okay, and yeah, I mean that's what we want to show. Okay, so there's greater probability of all of them being 0 than some subset being 0 times some subset being 0. Okay, so proof. So we define order D plus 1 tensors, T and S, by T of x0, x1, all the way up to xd is equal to the sum of I equals 1 to m x0i Ti x1 up to xd. Okay, and S of x0, x1, xd is equal to sort of the same thing. So I equals m plus 1 to n x0 I s I minus n of x1 up to xd. Okay, now why would we do this? We do this because we know what the bias is. So actually, strictly speaking, this doesn't actually use the inequality on the analytic rank. We're actually using this inequality on the bias. Okay, we know the bias is a probability, and it's the probability that some some d+1 tensor, if you just look at the last d coordinates and you fix them, it's if it's a linear form that is identically 0. Right? So what am I trying to say? The left-hand side is bias of t. T plus s, and the right-hand side is bias t, bias s. Right? Okay, I mean, I'll leave it up so we can stare at it together for a moment. All of these are 0 if and only if this, this plus this is identically 0 as a linear form of x0. And then bias t times bias s, that's this. So this one is this function being an identically 0 linear form, and this one is this one. Okay, so just, it's like proof by staring, kind of. Okay, so that's the subadditivity and one little corollary of it. And subadditivity will come in later when we do when we prove that the analytic rank can replace the partition rank in applications in some sense. Okay, so that'll be the content of the next video. Okay, see you next time.